So today we're going to talk about clustering. So far, the previous sessions, we were doing supervised learning, right? So we started with, we looked into example of regression and then followed that by classification. And today we're going to talk about clustering. So clustering, actually, by the way, clustering and classification are similar. In the sense that the task you are trying to do in classification is to classify a data point to a class or to group, class 1, class 2, class 3, class 4, correct? While in clustering, what do you do? Also, you are grouping data points into several groups. So classification and clustering, they look similar in the sense that after all, you are trying to group. Like, for example, if we go back to the handwritten digits, then we were classifying an image, whether it's going to go to handwritten digit 0 or 1 or 2 or 3 or 4. Now, if you do handwritten digit and you try to do clustering, what you do? You try to cluster the similar images, meaning those images that look like 0 should go to group 0. Those images that look like 1, similar because in shape, then they should go to cluster 1, and so on and so forth. So in the sense, they look similar, but the difference is classification requires labeled data set. You must have labeled data set. Okay, so when we go to the handwritten digit, there should be inside our data set somewhere information telling us this image is 0, this image is 1, this image is 2. Okay, if you have that type of data, meaning you have labeled data set, then you can go with classification here. But if you have unlabeled data set, then you can go with clustering. Okay, so again, the general idea looks similar, but the only difference whether your data set provides you labeled data set or not. If it provides labeled data set, then you can go with classification. If it doesn't provide labeled data set, then you go with clustering. Clear? So if someone asks you what is the difference between clustering and classification, hopefully now it's clear. So if we look to the example we saw earlier during the lecture for iris dataset. So if we have it labeled, of course, this is a labeled dataset. When we visualize it, now we know that this portion of data points belong to Virginica, for example. This portion of data points belong to versicolor, while this portion of data points belong to setosa. In other words, our dataset is labeled. Since it is labeled, then we can go with classification. But let's say we have none of these labels. We don't know which data point are setosa, which data points are versicolor, which data point are Virginica. We have a bunch of data points, which gives us like betal length and betal width. But other than this, we have no label. Then we need to go with clustering. Okay? So same problem. You can treat it, if you like, as clustering, where you ignore the label, or if you have the label and you would like to consider, then in this case, you go with classification. Now, of course, why you need to know this? Because clustering algorithms are different than those classification. In addition, the performance metrics are different as well. So let's look into one of the famous algorithms, which is called Kmeans. We're going to look into it through today session. Let's say we have the dummy data. So this is dummy data set. We have it here. How many clusters you can identify by observation? How many clusters can you identify by looking at this dummy data? 5, right? So we have group 2, 3, 4, and 5. We have 5. Now, in order to use K-means, actually it's quite simple. We need to use K-means from scikit-learn, and then we need to provide the number of clusters. So K-means requires you to identify how many clusters you like K-means to work on. So now currently using our observation, our naked eyes, we identified 5. This is why we have here 5. And then run the state, we set the value, to ensure that the results are usable. That means every time you should yield the same results. Now let's tell you how K-means work. K-means actually is quite simple algorithm. It's not difficult one. It's not complicated. K-means simply depends on the idea of having centroids or unit cluster. Meaning, each cluster of these that we said that we have 5, they should have a data point representing each cluster. a data point representing each cluster. These data points, we call them centroid. For each cluster has only one centroid. So here in this case, we identified k equals 5 clusters. That means we're supposed to have 5 centroids. Now, if we run Kmeans, let's say eventually Kmeans will find these centroids inside your data set. Today we're going to discuss about the steps, but let's say after running Kmeans, these are our centroids that Kmeans found. Okay, those that you see them in red, these are the centroids inside this data set. Now, after running Kmeans, if we like to assign data points into cluster, right? Because after we done clustering, we identified the centroids, which is the main part of Kmeans. Then let's say we would like to assign data point to one of these clusters. Let's say this data point. Let me choose different color. Let's say this data point. I'm not sure whether the data point should belong to this cluster or this cluster or this cluster. So I have no idea whether it should be here or here, this cluster, or this one, or this one. Now again, remember the centroid identified the cluster. So actually, eventually here we have probably this one cluster. This is another one. Okay, so you need to look where are the centroids. Okay, so we have 5. Anyway, now how Kmeans will decide whether this data point should be assigned to this cluster or any other cluster. Simply, it will depend on proximity measures, like median distance, meaning it's going to calculate how far this data point to each centroid. So it's going to calculate the distance, how far it is from this centroid, to this centroid, to this one, and this one. Then the shortest path, the nearest towards the nearest centroid, will determine where this data point will go to. Now, looking into this one, it's quite obvious that this data point is nearest to this centroid, correct? Therefore, Kmeans will assign this data point here. So this is why proximity measures were important earlier. We studied them because they have many applications, especially in clustering. They depend on proximity measures. Is it clear? So again, I repeat, firstly, Kmeans will find these centroids because these centroids will determine the cluster for each, the data points that each should belong in, will determine the clusters and their data points belonging into. Okay? Then second, once we need to assign data point to cluster, Kmeans will measure the distance, how far this data point, like in our example here, this one, to each and every centroid we have here. Then the shortest one, meaning the nearest centroid, will determine where this data point should be assigned to. Okay? Is it clear? Anyone have a question? Okay. So actually, Kmeans is simple, not difficult algorithm, and it's quite famous at the same time because it will yield the solution fast. It doesn't take long time to find the solution. Meaning, I mean the centroid. The centroid won't take long time to find. Okay, so here, as I said, we need to decide how many clusters, random state, and now this one in initial equals 10, because Kmeans may fail to find the best solution. Why? Why Kmeans may fail to find the best solution? Because simply Kmeans depends on the luck of initialization for these centroid. Of course, this is the final solution, but at first, probably, Kmeans will just randomly choose some data points to be centroid. Let's say, for the sake of argument, at first this was when you run first cycle, when you run Kmeans inside, it will maybe determine that the centroid is here. This is one of the data points for centroid. This is another data point. This is another data point for centroid, and here another data point for centroid. Now, having such solution, maybe eventually, maybe after running Kmeans fully, maybe it will find that this is the centroid. So this one will move to here. That's fine. This one might stuck here, because just one centroid need to represent these two. So it may eventually not go here. I mean, not shift this centroid to here and then shift another centroid to here. So in other words, maybe it will decide that this is a centroid for 2. And then here, maybe eventually will be shifted here, no problem. And these 2 may stick here. So we will have different clusters. Okay? Which looks good, but not very good. Because we know in advance that these should be two clusters, right? And these 2 should be 1, for example. So this one, we call it suboptimal solution. This is called suboptimal, not the best, but suboptimal solution. Okay, I cannot write here, but hopefully you got the point. So this is called suboptimal solution. Now, in order to avoid this, hopefully, this is why we request from Kmeans to run 10 times. That means it will find 10 solutions. 10 solutions. And then after all, Kmeans will give you the best solution among these 10. And hopefully that one of these 10 solutions will yield like this, the best solution, the optimal solution, rather than falling into suboptimal solution. Because again, I repeat, because it depends on the luck of initializing centroids for the first time. Because when it runs, this is the final centroid found. But at first, maybe they are any of these data points, can be, at the time of initialization. Okay? Now you understand why here we have 10. Okay? Not okay. Any question?
Why 10?
Sorry?
Why 10?
Why? Why 10? As I said, just we need to run multiple times Kmeans, meaning behind the scene, they're going to be finding Kmean 1, let's say. Kmean 2. Yeah, it's going to randomly assign centroid differently because behind the scene there's randomness going on. For initialization, for initializing, again, randomness where happen? Randomness happens during centroid initialization. Okay? So, as I said, maybe at the end we might find suboptimal solution. Maybe Kmeans will fail to find this. This is a good solution because we have 5 clusters and now each cluster have only 1 centroid. This is good one. But in case Kmeans not able, because during the initialization time, maybe it has chosen some centroids which are hard to modify later. Like if it has decided there's only here 1 centroid and then 2 centroids here, eventually maybe Kmeans will be fallen into this suboptimal solution and not try to find the best one. This is why, since the randomness will go around, maybe this time it will choose these centroids. Maybe at first Kmean 1. Let's say it has successfully found these. Let's say. But maybe second Kmean, this is a suboptimal solution, right? Maybe second Kmean will find the correct one. Maybe this one, this one, this one, this one, and this one. This is why we need to run Kmeans several times. So instead of running it manually by yourself, creating many Kmeans, just we have one hyperparameter or one let's say argument for Kmeans where you decide how many times you would like to run Kmean. And then Kmean, after finding all the 10 solutions, will give you the best solution based on performance metric called inertia. We're going to study now. Okay, any other questions? Any questions? Now, in order to get the cluster center, the centroid, we can call the parameter cluster center from Kmeans. This one will give you the position for the centroids. Okay. Now, if you notice here one more thing, when we call predict, of course, there is a function 2-in-1, fit and predict at the same time. Okay. Now, if we call fit and predict, meaning we are doing prediction after fitting, K-means will give you these numbers. What these numbers are for clustering. So for example, 4, 0, 1, 2, 1, 0, and so on. Actually, if you check how many unique values you have inside this white grid, you will find that you have 5, 0 up to 4, right? Why 5? Because we decided we have 5 clusters, A equal 5. Okay? So when you call mp.unique, it's going to give you 5 unique values. But what these values are, 0, 1, 2, 3, 4. Simply these value refer to the cluster ID. So 4 meaning the first data point inside X has been assigned to the cluster ID 4. The second data point in X has been assigned to cluster ID 0. The third data point in X has been assigned to cluster ID 1, and so on and so forth. So again, these are the cluster ID, cluster IDs, okay, for X, for assigning X. Okay? So you need to understand what these values are. Now, how to know where is cluster ID 4 and where is cluster 1 and so on. Then again, you refer to cluster center. These numbers actually, 0, 1, 2, 3, 4, they are referring to the index of cluster center. Meaning, if I say 4, like for the first X, the first data point has been assigned to cluster 4, that means you need to go to the index 4, 0, 1, 2, 3, 4. This is the cluster, the centroid for cluster ID 4. Okay? 0 here means this is referring to cluster ID 0. Where is centroid for cluster ID 0? This one. So you need to match with the index. This is just simply referring to the index. Okay? Okay, guys? Here? I hope so. Huh? So here we draw these centroids. We can visualize them. Of course, if you have new data points you'd like to assist or assign. So here predict, we're not predicting value, we are assigning. Okay, so please understand what's happening here. Instead of predict, like you are assigning X and U points into clusters. When we call predict, meaning we are assigning these data points to clusters. So in this case, Kmeans had decided that the first data point, this is the first data point, has been assigned to cluster ID 1. The second, also to cluster ID 1. Third data point, cluster ID 2, and so on and so forth. Okay? Now, what we are doing here is called hard clustering. Hard clustering. The way that when we call predict, this is hard clustering, by hard clustering. Just simply by calling predict, and predict is going to give us the cluster ID to each data point. But we have also soft clustering. Soft clustering meaning if you like to know the likelihood of this data point belong to cluster 0, cluster 1, cluster 2, cluster 3, cluster 4, all at the same time. You need to know the likelihood. Then you need to apply soft clustering. Okay, in hard clustering, just we need the final result. Just give me which cluster the data point should belong to. That's it. But in soft clustering, no, I'm interested to see the likelihood that this data point belongs to cluster 0 and all other clusters. Okay? So simply, in order to do soft clustering, in this case, we call the function transform inside Kmeans. Actually, here simply what Kmeans will do, will calculate the distance between this data point and all the other centroids. So we have 5 centroids, right? 5 clusters. So this is why if we calculate the distance, how far this data point from the first centroid, you will get 2.81. This data point from the second centroid is 0.33, and so on and so forth. So each row here represent the distance. Each row here represents the distances or this, the first data point, to the centroids. Okay, would like me to write? So each row represents the distances of a data point to all centroids. If you calculate, would you like to prove that the first distance is 2.82? Very, very simple. Let's open PowerShell. We do some math. So if we check, the first data point is 0.2, right? 0.2. What is the first centroid? The first centroid is minus 2.8, correct? So that means we need to take Euclidean distance, let's say. So minus 0.8 minus 0 is just 2.8, right? To the power of 2 is going to become positive. So 2.8 multiplied by 2.8. Anyway, then plus 1 minus 8, sorry, 1.8 minus 2. Then 1 minus 1.8, sorry, 2 minus 1.8. To the power of 2, just simply we multiply the same value again. We multiply again. Correct? Then finally, we need to take the square root, Euclidean distance. Now, in order to do PowerShell, we need to use .NET library called math, then sqrt. If you know C#, you can apply the libraries inside PowerShell directly. So this one will give us 2.807, meaning almost 2.81. Right? If you round this value, you will get 2.81. Okay, clear? So simply just we are calculating Euclidean distance between each data point and all centroids. Actually, it's interesting. If you look now here, which value is the smallest? Yeah, 0.33. This one corresponds to the distance to which cluster? 1. This is why when we applied hard clustering, it tells us 1. Shortest distance. How about this one? If we look to the third data point, simply this one, minus 3.3, these are the distances to all centroids. Which value smallest? 0.29. This one corresponds to the distance to which cluster? 2. This is why here it has shown us 2. Okay, good. Any question? Any question? Any question? No? So you're ready now for another quiz? For Kmeans? Again, the idea is simple for Kmeans. It uses proximity measures to find centroids first, and then once centroids are identified, then assigning data points to cluster by only finding the shortest path, or in other words, the nearest centroid, then that data point will be assigned to its respective cluster. Now, in order to measure the performance of clustering, we cannot use classification measures. So we cannot apply accuracy. If you remember yesterday, I asked you, or name 3 metrics to evaluate classification. Unfortunately, I think not all people answer. I don't know, I got even weird answers. But I haven't marked any paper yet. Huh? They are still here beside me. I haven't started yet. But we cannot apply accuracy, recall, precision, confusion matrix, because this is not labeled data set. Remember when we were calculating accuracy, precision call, confusion matrix, whatever, we depend on white true, correct? We requires white true, the label that we have inside our data set. Now we don't have white true, so we cannot apply any of those metrics. For clustering, we have different metrics like inertia. Please correct this one, that's just spelling mistake. There's no T here, just I-N-E-R-T-I-A. Inertia. Inertia is known as within cluster sum of square. Always figures can speak 1,000 words, right? And instead of reading this text, actually I posted here some pictures, but they're not showing up. If you just click and navigate to the links inside, then I can explain to you what is inertia. This is the equation for inertia. But anyway, let's look into figure to understand, right? As they say, figure speaks 1,000 words. Let's say we have this cluster, this data point. If you look here, we have 3 data points, and this is their centroid. And here we got another data points, 4 of them, and this is their centroid. Okay? Now, inertia, very simple. Inertia will go to each centroid. We have, of course, here we have 2 clusters, k equal 2, and it's going to go to the first cluster and calculate the distance between all data points in that cluster, their respective centroid. Meaning it's going to calculate the distance, let's say using Euclidean distance, how far to here, how far to here, to this data point, and this one. Okay, so after calculating the distance using Euclidean distance, just it's going to sum up these values. And then let's say we got some value V1, some value, by adding up or something, doing summation for all these Euclidean distances. Same way we go to the second cluster, and then we calculate the distance between all data points and their respective centroid. And then also we sum up these value, we get V2. Okay? Finally, inertia, just summing up these 2 values. V1 plus V2 will give you inertia. That's it. This is inertia. So you need just to calculate how far each data point inside their cluster to their centroid, adding up, summing up all the distances, then do again the same process for other clusters. And finally, sum all the values up, you get inertia. So inertia here in this case equal to V1 plus V2. Okay? Okay. And the equation is here. For inertia, what I said now, this is their equation. It sounds complicated, but actually it's not. So here we're looking for the distance, if you notice, the distance function, like Euclidean distance, between each data point and their centroid. Centroid of that cluster, A, that we are working on. And then we take all the data points we have inside that respective cluster. We sum up, then we repeat again for each and every cluster. Cluster 1, cluster 2, 3, and finally we sum all the values up. This will give us the centroid, the inertia. Okay, and this is, they call it here objective function because when Kmeans work, the objective is to find the best cluster that minimize inertia. So this is in short, and it's called within cluster sum of square. And it measures internally the coherent of clusters are, how much they are coherent. In order to get inertia, just simply we go to our K-means. There's a property called inertia underscore, and here we get inertia 2.11. Sorry, 211.5. Or you can call the function score. But function score will give you the value negative. Why? Because again, like if you remember, mean square error also it will give you negative. Because the people who designed this package, they had in mind when you talk about score, score means the higher the better, right? I mean, intuitively, everyone understands the score higher the better. Like you get marked for a course, the higher the better. But here, the opposite for inertia. Inertia, the lower the better. So just to differentiate this concept, they put negative. If you like to get rid of negative, just put minus here, and then you get positive. Okay? So why it's negative? Just of the design of the library. The higher, the better. But here, inertia, the lower, the better. Okay? Now, how to find the optimal value of K? This is an interesting question. Why? Because as we said, these require you to identify how many clusters you have. So here, by doing observation, we are able to identify how many clusters, right? By looking into this data set, which has disappeared. There's some error here. It's not defined. Need to run this one, this one. So by looking at this data set, we can see that we've got different data set. Okay. So we find that we have 5 clusters. By using our eyes, right? By using our eyes, we can inspect the data set. But this data set is small. You have has low dimensionality, has only 2 dimensions, x1, x2. But let's say your data set has 3 input variables, 4, 5, 6, then you cannot visualize, right? The maximum you can visualize probably 3D. Then how you become 4D, 5D, 10D, then cannot visualize. Meaning we cannot depend all the time on this way to identify how many clusters we have. Here it's okay because it's only 2 dimension, as x1, x2 only. Okay? So how to find the best value or the optimal value for K without visualization, without using this visualization? By applying inertia. So we're going to take advantage of inertia. And in order to find the best value, we're going to fit many K-means with different value for K. So here we're looking for K-means where K1 up to 9. So we are fitting many K-means with different value of K. So again, why we need all of this? We need to find the optimal K. Okay, guys, so let's carry on. So in order to find the optimal value for K, as I said earlier, we can depend on visualization. We cannot depend on visualization like this all the time. Because here we have small dimensionality number, only x1, x2. So we were able to use our eyes, our naked eyes, to identify or to observe how many clusters we have. But in case we have more dimensionality, then we need to use inertia. We're going to use inertia in order to help us to identify how many clusters we supposed to have. So here we took different values for K, starting from 1 up to 9. We fit K-means for, and then we collect inertia for all K-means, 1 to 9. And then you need to have one visual element of inertia as a function of K. So we show that what is inertia for each value of K. But actually, if you look to inertia is not very good performance metrics for one reason. Because inertia will keep dropping down no matter how many K you have. So if you keep increasing the value of K, inertia will keep dropping down. So then how we can identify the best value for K? Simply you need to look for the elbow. Look for the elbow shape. So here we can identify we have an elbow shape here. Then you check the corresponding K, which is 4. Okay? Clear? So again, inertia on its own is not so good because it keeps dropping down no matter what. So if you keep increasing K, inertia will keep dropping down. But we're going to use it as looking for the elbow shape inside the figure. This will help us to find the best value for K. Now, another metrics also can be applied to find the best value for K is silhouette score. Silhouette score has also formula, also is not showing up here, the picture, but we're going to look into it also through the lecture time, no problem. But for now, just let's understand what is silhouette score. Silhouette score is some formula been calculated for each data point inside the data set. So silhouette score is computed for each data point. And this silhouette score has a value range between -1 to 1, like correlation, right? Yesterday I asked you about correlation. So silhouette score also has value range between -1 to +1. But these values, what do they imply? I mean, what is the interpretation for these values? If you got silhouette score positive value close to 1, meaning the data point has been correctly assigned to its own cluster. Okay? If silhouette score near to 0, meaning the data point is very close to 2 clusters. So it is on the fence, let's say, or on the boundary of 2 clusters. This is why you can have silhouette score give you 0 or near to 0. If the value negative close to -1, then it says that this data point has been wrongly assigned to this cluster. Okay? Clear? Maybe I demonstrated again as I did, but now we have big class. So let's say here I have two clusters. Eventually, let's say here one cluster. This is another cluster. Now again, the silhouette score is going to calculate value for each data point. So each one of you has silhouette score. Okay? Let's demonstrate it on myself. Let's say I'm the data point and I need to check whether I'm assigned to the correct cluster or not. Assuming now if you check, let's say I'm closer to this cluster, and I have been assigned to this cluster. Now if I calculate the silhouette score, it should be close to 1, indicating that I have been correctly assigned to this cluster. Let's say I'm here, in the middle, between these two clusters. Now if I calculate the silhouette score, it's going to be equal to 0, because I'm border between two clusters. But let's say I'm standing here at the same time I'm assigned to this cluster. Now if I calculate the score, should be close to the, meaning wrongly been assigned to this cluster. I should be reassigned to this cluster because I'm nearer to this cluster. So this is silhouette score. Again, it's going to calculate value for each data point inside. Now, if you like to get the total silhouette score for all data points you have, then you have a function ready for you to use called silhouette score inside metrics. You give the data points and their cluster ID. So we take from Kmeans the cluster ID in order for silhouette score to calculate, see what is the corresponding value. So the total silhouette score for this cluster that we got here, all these clusters, is 0.66. Now, if you like to enhance, in case if it can be enhanced, then you need to look for higher silhouette score. Similarly, we can use this silhouette score in order to find the optimal value for K. So again, we train or we take the silhouette score for our labels, and then you can draw for different K. Calculate, we already have K-means, just we calculate silhouette score. Now in this case, you look for the highest value for silhouette score. In inertia, we look for the elbow, right? Because inertia will keep dropping down. But silhouette score, as you see, has a different way. You need to look for the highest value. Okay, here. So now you have inertia you can use, you have silhouette score, can help you to identify how many clusters you need for your data set. But nobody asked, is K equal 4 good? Is it logical? Eventually, or actually initially, we said that actually it should be 5. Correct? See, nobody noticed. It should be 5, but yet inertia has said 4. Actually, doing this method is not perfect. It's giving you 4 is not perfect. If you look to the silhouette actually gives you more information that these 2 points have the highest value for K equal 5 and K equal 2, right, for silhouette score. Now, in order to have final determination whether to go with 4 or 5, I'm not going to explain, you can refer to your textbook. He already explained for this example what you need to do further to determine the final, whether you need to go with K4 or K5. And actually, he has found eventually that K should be 5. Okay, now one shortcoming for Kmeans. If you look to our data set that we worked on in this example, they have the shape of globe, right? They have the shape of globe, like circle. You can think of it in 2D. So Kmeans prefer clusters where the data set looks like a globe. So like this example, Kmeans is good. For this data set, Kmeans is good because the shape of your clusters are globular. Okay? Now, if we go to another data set, like this one here, presented in this case, okay, and apply Kmeans would fail to find the correct cluster. Now, here it's obviously that we have 2 clusters, right? Obviously, we have 2 clusters. This is one cluster, right? And this is another cluster. But if you apply Kmeans will fail to identify this cluster. Actually, if you insist on applying Kmeans, by all means, go try on your own. Kmeans probably will give you this cluster. Say all these data points belong to one cluster, and all the other data points belong to the second cluster. Because again, K-means prefer globular shape, should be globular shape, okay, when identifying its cluster. So K-means for this data set will fail to find the correct clusters. This is why we are looking for another algorithm called dbScan. dbScan depends on the density, is one of the density-based algorithms, meaning it will try to find the high density inside the data set and then link all these, let's say, determine that all these data points should belong to one cluster. But let's understand how dbScan works. dbScan is also simple, not difficult one. Also, I need a figure. Also, it's not showing up here. You can just search. Let's look into Google for one picture. Then I will explain to you how dbScan works. Okay. So here we have different data points. These for our data set, all of them: the orange, the blue, the yellow, and etc. So ignore the color. Just these are, let's say, a sample from our data set. Now, dbScan, in order to work, it has first to identify each point as one of three, whether it is core point or border point or noise point. So again, the first step in dbScan is going to identify whether the data point is core point or border point or noise point. How? If you look, in order dbScan to operate, if you remember, K-means we have to provide the value of K. For dbScan, you need to provide epsilon value, the radius, and the minimum sample of points. These two in red you need to provide before using dbScan. Okay? This is why here also, if you look, when we use dbScan, we have epsilon and minimum sample of points when you need to use dbScan. Those two values will help us to determine whether the data point is core, border, or noise. How? Simply by using the epsilon, dbScan will be able to use it as radius. Let's say here I got this circle based on the epsilon. I'm going to use. Let's say here I got some data point. Now, how dbScan works? If you check this circle, right, based on the epsilon, let's look at this data point, and then we count how many data points are inside this circle. How many data points? 3, including the data point itself, become 4, meaning we have more than the minimum sample point, which is 3, correct? In this example, since you have fulfilled the minimum sample point, then this point is considered core point. Okay, the yellow one is core point. How about taking other point? How about this one? Okay, how many data points we have? We have only one. In addition to the data point itself, become 2. So we have 2 data points, which is less than 3, the minimum sample point. Right? That means this is not core, cannot be core. Now, the only decision left is whether this data point is border or noise. In order to call the data point border, in this case, it must have neighbor of core point. So we check, is this point, does this point has a neighbor of core point? Yes. Since it has neighbor of core point, this is border. Okay, clear? Let's take another example. How about this one? Okay, so again, this example, I think the data point itself shouldn't be counted or more, because your textbook, the other textbook says including the point itself. But according to this example, the point itself is not included. So forget about this point. Now again, how many data points we have? We have 2, right? Forget about the point itself, we have 2, which doesn't fulfill the condition for minimum sample point, which is 3. Then we need to ask ourselves the following question. Does it have a neighbor of core point? No, it doesn't have neighbor of core point. Here we have core point, but this is not neighbor for this one. Why it's not neighbor? Because it's outside the radius, outside the circle. So it's not neighbor. Since it doesn't have neighbor and it doesn't have core point neighbor and doesn't fulfill the condition, then this is noise. So the orange are noise, the blue are border point, and the yellow are core point. Okay, clear? So this is core, as we said, this is border, this is also border, this one is noise, it's quite clear, this is noise, right? This is also noise, and so on and so on. This one, neighbor, this one. Okay, clear? So again, at this stage, DB-scan will identify each data point as one of three, whether it's core point, border, or noise point. After identifying those core points, now those core points, DB-scan will use to identify the cluster. How? It will look for all the core points that are neighbors to each other. So now if we take these two core points, are they neighbor? No. I think this one not showing, right? Okay. So if I check the shape here, these two core points are not neighbor. Why? Because they don't fall inside the circle of each other. Correct? Since they're not neighbor, then these DB-scan will consider that this is one cluster, this is another cluster. At least this core point will be assigned to separate cluster. Now, in order to have them as into assigned cluster, we're supposed to have core point in the middle to connect them. Assuming I got core point here, then this data point will become neighbor to this, and this data point becomes neighbor to this, right? So eventually, DB-scan will identify these core points as one cluster. Okay, so they will be assigned these core points into one cluster, if you like very much. Okay, in order to determine the core point, we need epsilon. The value of epsilon will determine. Because you need to use epsilon in order to draw this circle, the radius. Okay? Then after you draw this circle, you need to identify how many points fall inside the circle. Of course, this one doesn't exist. How many data points? You need to count them. How many? In this case, we have 3, excluding the point itself. Or if they become, anyway, they fulfill the minimum points threshold. Since they fulfill the minimum points of threshold, then this data point is core point. It's going to be considered core point. Then you use epsilon again. You draw radius for all the data points you have, all of them. You need to draw a circle and then count how many data points they have inside. If they fulfill the condition, this one, then they are core points. If they don't, then you need to check their neighbors, whether their neighbors have core point. If they have core point, then they are border, like the example here. This is border point. If they don't have core point as neighbor, then they are noise. Okay? Is okay now? Okay, where the point you stuck to? Yeah, next to him, also that fall inside the circle. They have to fall inside the circle. Now, this epsilon is small. If you enlarge epsilon, maybe eventually you will be able to include the other one inside it. I cannot enlarge. Okay, but because of this epsilon, we cannot consider this as neighbor. Because if you check inside this circle, is this core fall inside the circle of this core point? No. Since they don't fall, DB-scan won't be assigned them together into one cluster. In order to be assigned to the same cluster, they have to fall inside, they must be neighbors. How to be neighbors? There are 2 ways. Either you increase epsilon here, so the circle becomes bigger, so that this data point will fall inside, or maybe if in case we have another data point happens to be, in case I'm saying it, just for the sake of argument, if we have another data point, then this point will become neighbor to this, right? No, this is now core point. It has to be core. That's why I color it yellow. So it has to be core. So assuming that I have another core point here for the sake of argument. Now this core point has become neighbor to this core point, right? So they can be identified into single cluster. But also this point is neighbor to this, right? You check the circle, this data point also fall inside the circle for the second one. So it's also neighbor for this core point. So eventually DBScan will identify these core points into a single cluster. Clear now? Any other question? Let's check. Anyone posted anything here? No question. Super. Okay. Now, after identifying the core points and setting clusters, DBScan will ignore the noise point. Noise point will be ignored, of course, and the border point will be assigned one of according to their nearest cluster. Okay. So now here we have one cluster, so all these data points will be assigned to this cluster. I mean the yellow one, the one I draw here. Okay, because they are nearer to this, and this is the only cluster we have anyway. So again, I repeat, 4 points will determine the clusters that we have. Second, the noise point will be ignored. The third, the border point will be assigned to their nearest cluster. This is DBScan. That's all. So in order to use very simple, just assign value for epsilon and minimum sample point with fit. Now, if we check the tables like Kmeans, will assign us, will give us the cluster ID. But in addition, you find that there's -1. -1 indicates the corresponding data point is noise, is anomaly. Okay. So again, I repeat, -1 doesn't mean we have cluster ID -1. -1 means the corresponding data points is considered anomaly, outlier, noise. Okay. So please, if you like to write, -1 indicates that corresponding data point is noise. In other word, outlier. In other word, anomaly. Anomaly. So in this case, we know which data points are noise. But how to know which data points are core has been considered as core? You call core underscore sample underscore indices. So here, this is an example showing you corresponding data points. This is the data point index inside the data set. These data points are core. So now we know which data points are outliers, which data points are core. The remaining data points are the border. Okay, so components also you can call, it is a copy of each core sample point found. If you like to get the data points immediately, just you collect them, then you call components. Okay, so components, this one will give you the data points inside your data set, the training data set, which are the core points. Okay, so these are a copy of core points in your training data, which actually correspond to the core sample indices. Because if you take these indices and look inside your training set, will give you these components. Would you like to try? For example, if you take this one, so our data set is called X, right? Is it X? X. So if we check inside X for the first one, need to run all. Okay, notice. So this is the first core point, and already inside component immediately has given us the core point. So here we can get the indices only for the core point. Here we can get the core point themselves. Okay. Now if we plot the figure, now DBScan, as I said, depends on 2 values you need to assign, epsilon and minimum sample point. And this can yield you different results. For example, If you have epsilon equals 0.05 and minimum samples is 5, then dbScan will identify these clusters. So how many clusters we have? 1, 2, 3, 4, 5, 6, 7. We have 7 clusters. If you assign epsilon to 0.2 instead, then dbScan will be able to identify. Because epsilon will determine the width of the circle to assign all the points into a single cluster. Okay, clear? Now, how to find the best value or the correct value for epsilon, I'm not going to discuss. You can search on the internet. It's not simply finding. There's a method you need to apply and then draw a figure. That figure will give you the value for epsilon. Which value for epsilon you need to choose. The last section we're going to discuss today is called hierarchical clustering. Hierarchical clustering. If you look to Kmeans, for example, Kmeans is called also partition algorithm, partition clustering. Kmeans is also called partition clustering algorithm. Meaning, what do we mean by partition? Partition means K-means will assign each data point to a single cluster. Cannot tell you that this data point belongs to cluster 1 and cluster 2. In other words, there's unnested, right? So meaning the data point will belong eventually only to one cluster. Cannot be nested, like nested loop, where you have data point belong to more than one cluster. If you like to have nested cluster, then you need to apply hierarchical clustering. Hierarchical clustering can be used. It can give you nested clusters. So if you notice here, some data points, how they are getting merged into separate, different clusters. So here C3, yet the same data point C3 has been merged to C4, and so on. So these data points will be nested in separate, different clusters at the same time. So how to look at this one? If we look to this figure, this will help you to determine. Now for hierarchical clustering, we have two methods, agglomerative, divisive. Almost same, but just the way they start to operate. Let's look into agglomerative in this example. Agglomerative works as follows. First, it will consider each data point inside your data set as a cluster on its own, as a cluster on its own. So at first, we had 7 data points. You check here. At first, we had 7 data points, correct? So each one of these will be considered as a cluster on its own. Then it will apply again Euclidean distance proximity measures to measure how far these data points from each other, and the nearest data point will be merged together. So in this case, we see that P4, P5, and P6 are the nearest, correct? So they will be merged together under C1. This is one here under dendrogram. You can see the vertical line showing merging. That means merging has happened. This is C1, where we merge P5 and P6 together. Then later, when we calculate the distance again, hierarchical clustering will find that C1 and P4 are the nearest to each other. And then they will merge them up into C2. Okay, so again, merging here, C1, 4 becomes C2. And then calculating distances again, you see how proximity measures are important. Then P1 and P2 will be merged, are nearer to each other. Then they will be merged together, forming C3. Cluster 3, this one, C3. Then again, calculating the distances will yield that this cluster is nearest to P1. So these two will be merged together to C4. So this is C4. And then C2 with P3 will be merged together to C5. As you see here, C5. And eventually, C5 and C4 will be merged together, forming C6, the last one. Clear? This is hierarchical clustering. Is it difficult? You see how it's nested? Data points like, for example, P5, P6, they belong to C1, C2, C5, and C6. Correct? So this is why we call it nested clustering. I cannot write difficult. It's like primary school. Okay, clear? This is hierarchical cluster. So let's see the figure here. They should look the same. Eventually, like what has been done. So started with B5, B1, C1, then together C2, then this one is C3, then together C4, then these together C5, and finally C6 all together. Okay? Now we will look to the details of the algorithm later, but this is the algorithm anyway, how it works. Now, how to determine the number of clusters? Because after all, always they will start from data points or clusters on their own, and eventually you will have one cluster at the end. Because you keep merging until you have one cluster. Then how many clusters we have? In order to determine how many clusters you have, you need to decide what is the threshold for your Euclidean distance here. If you say my Euclidean distance threshold is, let's say, 1.8, meaning here, then you draw a line and you count how many vertical lines you crossed. Then 1, 2, 3, 4, 5. That means if you do this Euclidean distance will give you 5 clusters. If you take the cutoff 3.8, then this one will give you 3 clusters. If you take 4.5, it's going to give you 2 clusters because you're going to cross 2 vertical lines. Okay? Clear? So hierarchical clustering by default doesn't require you to provide how many clusters you have. Then after by generating dendrogram, then you can decide how many clusters to take. Usually people will look for the long vertical lines in order to decide where's the cutoff for the Euclidean distance. Okay? But anyway, the implementation here for scikit-learn, at least here, the one that we have. So here we have dummy example, and we're going to use agglomerative from scikit-learn. Here, by default, actually, it will look to the number of cluster behind the scene. So if you check agglomerative, has one argument. It says number of cluster, by default is 2. You need to hide that one. Okay, so you see at the top, number of clusters by default is 2 for this implementation of the algorithm. But anyway, naturally, hierarchical clustering doesn't require to provide the number of clusters. Now, in order to determine the distance, to calculate the distance between different clusters, because everyone knows how to calculate the distance between 2 points, right? Between 2 points, how we calculate it? Here one cluster, here another cluster. How we calculate the distance? There are several ways. Or think about like states. If we have separate states, then how we calculate the distance between these states? There are several ways. Maybe you take the nearest point from one cluster to the second cluster, or maybe you take the city center for each state, then you calculate the distance. So there are several ways. We're going to start to talk about during it. This is why we have what's called linkage. Linkage will determine how to calculate the distance between different clusters. For data point, everyone knows, because we use Euclidean straight away, we know. But for clusters, we need to identify the linkage type, which will determine how to calculate the distance between the clusters. We're going to talk about later on. It's very easy, not difficult. The concept is quite simple. Anyway, we're going to discuss later on. Any question? So this is all for our practical session today for clustering. Hopefully now you understood what is clustering. It's unsupervised learning. Why it's unsupervised? If you notice here, when we call fit, we provide only X. There's no Y, right? In regression and classification, you have to provide X and Y. Since you can only provide X, then this is again unsupervised learning. You don't need to provide labeled data set. So our data set simply like this. We have no label. Nothing tells us which data point belongs to which cluster. If you have the data set which tells you which data point belongs to which cluster, meaning it's labeled, then just apply classification. You don't need to go with Kmeans and so on.